In this video, we are going to talk about cross-validation, and maybe this could be your start to learning something new. And I am Saurav Agarwal, you are watching Datahat, unfolding mystery with data. We bring this channel together to unfold the mystery of data and learn data science and its concept. So what are you waiting for? Let us get started and make a promise of learning new ideas, new content. In this video, we are going to talk about cross-validation, what is the need for cross-validation, and what are the various popular techniques of cross-validating your machine learning data. So understand first of all what we mean by validation. When we talk of validation, it refers to the techniques of assessing the model's performance. Understand that when you train a machine learning model, you train it on a subset of your entire data set, which we call the train set. Now you want to estimate the performance of this model on a separate subset which is not previously seen during training, right? There are two techniques of keeping out the separate subset which is not previously seen. The first, in which we make two splits. The two splits are called the train split and the test split. So there the test data set is kept entirely aside from your training data set, and test data set is used for validating the performance of the model. Now what happens in real productionization, or when you go for real experimentation, if you try and use this test data set each time for your performance, your model could be less reliable. So instead, we make a three split, or we have three different subsets known as the training set, the validation set, and the test set. The training set is used for training your machine learning model in any iteration. The validation test set is used for validating the performance of your model after every iteration, and the test set is preserved for the final validation when you move your model to productionization, right? So from here on, whenever we talk of test set, that would refer to the validation set, right? Understand, we are going to use it interchangeably here. The same concepts that we apply to validation set can be applied to your test set. So again, to remind you, whenever I talk of test set here, that would refer to your validation set in your three subset category or three subset examples. Now talking of cross validation helps us to reduce the chances of overfitting. How? Because in cross validation, instead of having the subsets, like having a train set and validation set divided into two two chunks, you have multiple different groups or multiple different subsets which are grouped together to form the training set and the validation set. This would help you reduce your chances of having bias in your overall performance and increase models reliability. Now let us talk of some of the popular techniques in cross-validation. Remember that this list is non-exhaustive. There are various other techniques of cross-validating as well, but just to understand the most popular techniques, we will discuss 6 of them here. So first example is a holdout cross-validation. In the holdout cross-validation technique, your test set is kept entirely separate, and there is only one iteration for testing the performance of your model. You have a train set which is fixed, you have a test set which is fixed, and you train your model on the training set and you measure the performance on the test set. Okay, here the chances are the model could have some bias because certain characteristics which might be present in your test set here would never be seen by your training data. Next up, we go for the k-fold cross validation. So when we talk of k-fold cross validation, here instead of having two splits, we split our entire data set into k splits, right? These k denotes the k in k fold comes from the number of splits that we make for our data. Okay, say for example, if we have 10 splits in our data set, that would be 10-fold cross validation. So now what happens? Depending on the value of k, there would be k number of iterations for measuring the valid performance of your model. In each iteration, we select, let us see based on the example. Say here we take an example of 4-fold cross validation. So we have 4 different splits. So in each iteration, we take k minus 1 split or k minus 1 splits as our training and 1 split as our test. Again, remember, here whenever we talk of test set, that refers to the validation set. So we have 3 splits for the training, 1 for the test. Similarly, in the next iteration, we will change our test set and take the other split as our test set and the remaining 3 as our train split. So this process is iterated over k times, and the performance of the model is taken as the average performance in all these iterations. So one of the advantages of k-fold is it allows you to reduce certain bias in your model, and also certain characteristics which might be present in a particular split would very well be taken up by your test training in 3 iterations or in k minus 1 iterations. Stratified k-fold. Now, stratified k-fold is built on top of k-fold cross validation. The biggest advantage of stratified k-fold is each split is a representation of the data in itself. So if you take any split, it would try to mimic, or it would try to represent the data distribution of the end. It will try to represent the entire data set distribution. Okay, so when we talk of stratification, it is usually used in cases of, say, classification examples. Say when you have, say, class imbalance, your positive class is 60 constitutes 60% of the data, whereas the negative class constitutes 40%. So each of these splits would have the same distribution for your class imbalance: 60-40, 60-40, 60-40, 60-40. And in each iteration, similar to k-fold cross validation, we take the different splits and compute our average performance. Okay, as you can see from the image here, we had the class distribution of, say, 4 classes. C1 is 15%, C2 25, C3 30, C4 30. So for each of these splits, we'll see we'll have the same class distribution. This is the advantage of stratified k-fold validation. Next, we talk of leave p out cross validation. In leave p out cross validation, assume your entire data set has n data points or n number of data points. Now, out of these n number of data points, you sample out p data points as your test set, and remaining n minus p will form your training set. Now this process is repeated over how many iterations? NCP iterations, because of permutation combinations. So in order to allow each data point in your data set to be a part of test set at least once. So it will ideally be the seal of NCP iterations. So say for example, if you have 4 data points and you have p as 2, so it will be 4c2. 4c2 is nothing but 4 factorial by 2 factorial by 2 factorial. Okay, you can just learn about permutation combination in as part of the separate exercise. Here we are not going into the details of it. So what happens here, we are taking out each time a sample of p data points out of n data points and considering our validation set accordingly. A similar example, or we can say a specific a specific example for leave p out cross validation is leave one out cross validation. So as you can understand from the name itself, instead of sampling out p data points, we sample out one data point each time. So you can also understand that this is computationally very expensive. Just selecting one data point out of n data points in every iteration and computing, so the number of computations would rise manifold. Okay, so far we discussed of the the various splits or the ways of cross validation in usually your classification examples, where you have independence. One of the primary assumptions of these splits are that each split is independent of other splits. There is no dependence of one split with respect to the other. However, when we talk of time series data, as we know, in time series data, each portion of the time or each time frame would be dependent on the previous time frames. It is having a dependency based on the ordering or based on the time step, right? So there, having such an assumption that each split is independent of each other is non-trivial. Okay, so what we'll do is we'll use a separate type of cross validation technique, which is known as time series cross validation technique, or it is also known as rolling cross validation technique. Now, and to understand this simply, we are taking an example. Consider this your data set having time range starting from t0 to tn in this order. What we will do is, in each iteration, say we are making a split we are making a certain, taking a sample of the data set starting from t0 till tk. Now what we will do is we will split again in the chronological order for the train and validation sets, or train and test sets here. In the next iteration, whatever was there in a validation set will be included in our training set, and whatever comes after tk time step, say for example a time span of p, so tk plus p, up till that time step we'll have our validation set. So it will, the validation set will move forward in time, and whatever was left behind will be included in our training set. So in each iteration we will be able to maintain that dependency of time here. And again similarly we'll take the average of your performance, or you can also take a weighted average of the performance based on the rate or the fraction of the data sampled each time. So this technique is very popular, and often people confuse and make a split in terms of like in terms of a normal split, where you assume that there is no dependency between the splits. Also from an interview perspective, like your interviewer is going to ask you that how are you going to cross validate your time series data, and why you cannot use k-fold cross validation or stratified k-fold cross validation. Now you know it, and I'm sure you're going to ace that question whenever it comes to you. Okay, so the last technique that we are going to use is, it works slightly differently from whatever we discussed so far. So so far what we were focusing on, we were focusing on sampling our validation set, or sampling out our test set, and then picking up the remaining as a train set. Now Monte Carlo cross validation, what it does is it samples out your training set first, and whatever is left behind is your validation set. It's just the difference in the approach, nothing much difference here, and nothing it's not that it gives you very good performance, or it gives you any improvement in performance as such. It's just the different approach that you apply to the technique. Okay, so hope far you learned the 6 techniques of cross validation: the holdout cross validation, k-fold cross validation, stratified k-fold cross validation, time series based cross validation, leave p out cross validation, leave one out cross validation, and lastly and the least important, Monte Carlo cross validation. So hope you enjoyed the lecture. If you're new to the channel, don't forget to subscribe, hit the bell icon, share it with your friends and data science enthusiasts, help them out, and see you in the next lecture. Have a nice day. Bye bye. Jai Hind.